In conventional physics and mathematics, a non-terminating decimal, or a divergent equation, indicates a failure state. A manifold lacks compactness, or a function breaks down into an infinite spray of numbers. The theory of infinity, or TOI framework, treats infinity as a foundational, generative bedrock, an infinite continuous space from which bounded realities are actively extracted. When a stable structure successfully seals within this space, it forms a golden set, a bounded stability sector characterized by convergence and mathematical closure. The topological hinge where an operation hits the set's physical limit is called not infinity. This event acts productively, forcing the system to introduce a missing residual carrier to balance the equation or retype the math to become valid in an adjacent structural loop. To govern these transitions, the framework employs the friction versus fiction protocol. This strict auditing rule demands that actual topological mass exchange, the friction, be distinctly separated from visual projection artifacts or unit mode traps. Applying this protocol reveals that numerical anomalies are structurally devastating fate checks. They expose exact theorems of phase preservation and topological mass exchange. This rigor is required when auditing the reciprocal Fibonacci quadratic gates. These are highly volatile topological systems, generating immense mathematical tension. This diagram simulates raw solver output for these continuous equations. The calculation yields massive chaotic integers, including a staggering discriminant of 24,307.5. This specific value under the quadratic formula's square root dictates the root's behavior. Standard systems process these equations, outputting nested radicals and bloated fractions. This scalar camouflage mathematically obscures the underlying discrete generator blocks. Dividing that massive 24,307,705 discriminant by 55, the 10th term in the Fibonacci sequence, known as F10, leaves a remainder of exactly 0. The resulting quotient is the precise integer 436,431. This perfect division indicates a structural factor lock, meaning the massive output is a highly constrained parameter. To determine the exact topological coordinates causing this lock, we must decompile these continuous shells to find their exact integer boundaries. We achieve this through apophatic decompilation. This is a methodological process that pushes a continuous mathematical output backward through its inverse boundary operator, collapsing fractions into whole verifiable integers. This technical source image shows the continuous projective boundaries, starting at the top with the family A acute gate. The generating equation places advancing Fibonacci sequence terms in a reciprocal arrangement, forcing spatial asymmetry with fn+2 and x squared in the denominators. To normalize the equation, we force an inward spatial collapse by multiplying the entire expression by its advancing spatial limit, f of n times x squared. This single operation clears the fractional denominators. The continuous reciprocal shell collapses into an exact quadratic integer polynomial, exposing the discrete math. This inward collapse has an ascending counterpart, the family B grave gate, shown in the bottom half of the image. The same decompilation process is applied here. The continuous boundary is multiplied by its respective spatial limit, f of m times y squared. The denominators clear, yielding a parallel exact integer polynomial that governs the ascending topological loop. Because these transformations map directly to exact polynomials without fractional drift, they serve as enclosing boundary conditions. They are securely registered in the system's ledger under the parent exact structural role. We can now evaluate this algebraic shell at a specific sequence rung, n equals 10. This rung utilizes the fundamental Fibonacci masses of 55, 89, and 144. This diagram illustrates the substitution process. By plugging 55, 89, and 144 into the generalized equation, the boundary resolves into the specific polynomial x squared plus 4,895x minus 7,920 equals 0. Applying the discriminant formula to these exact coefficients calculates out to 24,003,705. This proves the massive numerical anomaly originates directly from the polynomial structure. Factoring out the initial Fibonacci mass of 55 isolates the bracketed integer 436,431. This value is the exact internal phase tension of the mathematical shell before it is scaled by the sequence's advancing mass. This perfect divisibility confirms that massive solver outputs reflect exact finite-rung topological limits. They are high signal indicators of deep structural exactness. With the internal phase tension isolated, we execute a structural test. We divide the exact tension integer, 436,431, by the squared spatial boundary of the subsequent sequence rung, which is 89 squared, or 7,921. This division visual shows the resulting quotient, 55.03737. The operation cleanly separates into the whole integer 55 and a distinct decimal tail. The integer 55 is the exact mathematical seed rail for the 10th Fibonacci rung. By forcing this division, the operation has successfully unzipped the active golden set to extract a deep-passed discrete anchor. The remaining decimal, 0.03737, is an exact Lucas number alternating parity residual. A Lucas number parity term is a related integer sequence used here to balance the exact mathematical remainder of the extraction. Because this extraction leaves a strictly defined, predictable residual, it achieves theorem-bearing status. The ledger logs it as a child exact closure, proving that topological tunnels traverse the infinite sequence. This structural rigidity extends to the equation's roots. When solved, the decompiled polynomial yields massive negative escape channels, such as negative 4,896.617. These roots are strictly tethered to the positive golden roots by the J1 zero-sum balance dynamic. This dynamic is an accounting mechanism that enforces the conservation of nothingness by requiring simultaneous positive and negative balancing. This side-by-side visualization shows the decompiled acute and grave gates for the n equals 10 rung. Both equations share an identical linear coefficient of 4,895. By Vieta's formulas, the sum of the roots for these gates must equal its inverted coefficient, exactly negative 4,895. The math balances perfectly. The positive golden root is 1.617, and the negative root is negative 4,896.617. Adding them together yields exactly negative 4,895. This balancing scale demonstrates the J1 dynamic in practice. The mirrored 0.617 decimals act as the precise mathematical friction to cancel out, conserving the parent shell's algebraic identity. The linear coefficient 4895 serves as the formal hinge, structurally locking the acute and grave gates together. These massive negative numbers function as structural counterweights that close the topological loop between sequence boundaries. The theory of infinity takes the markers of mathematical breakdown, divergent outputs, and non-terminating decimals, and recontextualizes them as rigid boundary laws. Equations that project continuous numerical chaos are subject to decompilation. Once the fractions are cleared, what remains is a perfectly sealed zero-sum combinatorial engine. Apophatic decompilation identifies mathematical infinity as a structurally regulated engine, where every operation adheres to an exact geometric ledger. By refusing to discard fractional remainders and auditing the friction within the data, we reveal the exact discrete origins of our mathematical reality.